Hi, thanks for attending this virtual talk on distributed signal detection under communication constraints. I'm Clement Canonne, and this is joint work with Jayadev, Acharya and Himanshu Tyagi. So this work is about, as the title suggests, distributed signal detection. There is a high-dimensional signal, call it mu, that we want to measure, but we don't get to observe mu exactly as there is some white noise, eta, on top of it. Equivalently, we observe a sample from a high-dimensional spherical Gaussian and are interested in its mean mu. This is sometimes known as the Gaussian location model, since the mean mu is the location of a high-dimensional Gaussian. And here, when I say high-dimensional, I really mean it. The dimension d in applications, especially modern ones, can be very large. And we will want to consider this problem in a distributed setting where communication is a bottleneck. So there will be some extra constraints in the problem we are actually considering. But let's start without those constraints to give a sense of that landscape. So the first natural question we may want to solve is to estimate the signal, that is to learn the mean mu, say in L2 loss to error epsilon. For that, it's actually well known that d over epsilon square observations are necessary and sufficient. And further, the simple empirical estimator achieves that sample complexity. Again, just to be clear, through this talk, I will consider always a constant probability of success, say 99%. So that's good. That's for estimation. But what could ask the detection analog of this question, that is testing whether there is a signal at all or it's just white noise. So the goal is to accept or reject the null hypothesis that the mean mu is 0 versus the alternative that no, the mean has magnitude at least epsilon. For that hypothesis testing question of signal detection, it's known that square root of the dimension over epsilon square observations are necessary and sufficient. Again, even like a simple estimator, namely thresholding the empirical estimator for the squared L2 norm of the mean, will achieve that sample complexity. Note that here it's like much cheaper than learning the signal mu. We save a square root d factor between d over epsilon square and square root d over epsilon square, and d is really, as I said before, large. That's great. As we just saw, for signal estimation and detection in the Gaussian location model, we have tight bounds on the sample complexity. Assuming, of course, that we do get to observe the entire samples from the high-dimensional Gaussian, which brings us to the distributed setting. What happens when the n samples, the observations, are distributed among n users, each user with one observation, and those users can only send some short summary of their observation to a central server? That's what this talk is about. We are going to consider the signal detection question, but when the central server only has access to a few bits of information from each sample. So more specifically, in this setting, we have n users, which independently of each other make a measurement of the unknown noisy signal. And then they can only send a short, think L-bit message, to a central server, which tries to perform the signal detection task, that is to decide whether the unknown mean has magnitude at least epsilon. Importantly, here we will only consider non-interactive protocols. Think of it as the case where there is a clear asymmetry between users and server. For example, cell phones versus data center, or a fleet of small sensors versus a central server. So the goal is to find the best protocol for the users to compress their observations to L bits, so that we need as few observations as possible. When I say as few as possible, that will be as a function of all the parameters. So the dimension d, the distance parameter epsilon, and the number of bits L available to send for each user. And think of L as small, much smaller than d. Now there is a distinction that I haven't mentioned yet, because it only appears in the distributed setting. Namely, sure, the users cannot interact. They still, in some situations, have a common random seed they could use to randomize their messages jointly. For instance, that seed could be specified ahead of time or broadcast by the server once in a while. That seed is, of course, independent of the measurements the users make, the samples. So we have two flavors of protocols. Those where there is no common random seed available to the users. I'm going to call that private coin protocols. And those where there is a common random seed, public coin protocols. At this point, I'd like to mention there is another paper I had called this year, of which I'm a co-author, paper number 96, which considers this type of distinction for a different distributed testing problem. What if the random seed is very short? If you have time, I really encourage you to check it out. So this is the setting. What exactly now do we get to prove in this distributed L-bit message setting? At that point, we can do that because it's a video and it's online. I encourage you to stop the video for a minute or so and try to guess what the right answer is. We've seen before that without communication constraints, it was square root dimension over epsilon square. So what does it become now? How does the answer scale with the number of bits, L? And since I've spent one slide introducing that distinction, does having a common random seed actually help? So here are our results. We prove some upper bounds for private coin and public coin protocols, as well as some lower bounds. The lower bounds will hold for some restricted parameter regime or some restricted class of protocols, but we see them as strong evidence towards our conjectures, and the conjectures are the lower bounds, the true lower bounds match the upper bounds we show, meaning our algorithms are actually optimal. So to pass these upper bounds, for private coin protocols, we give two of those algorithms. D to the 3/2 over epsilon square L, take that, and the minimum with D over epsilon 4 users are sufficient. And don't see the first term as square root D over epsilon square times D over L, meaning this is the thing without constraint multiplied by a blow-up factor due to the constraint, which is D over L. For public coin protocols, we give a protocol that achieves D over epsilon square square root L. And again, you can see it as square root D over epsilon square, what happens without constraints, times square root of D over L, the blow-up factor. So the blow-up factor for public coin protocols here is square root of what it was for private coin protocols. The lower bounds are specified here. It might seem a bit strange the way they're phrased, but essentially the first one, D over epsilon 4 for private coin protocols, is for a restricted class of protocols that is natural, but amounts to forgetting about some information about the samples. In the public coin case, we show a D over epsilon square L general lower bound, which is not quite tight, but holds for all public coin protocols for small enough L, as well as a tight bound of D over epsilon square root L users, but only for a natural yet restricted class of protocols. And as I mentioned, we conjecture that all our upper bounds are tight, and we provide evidence in the paper for this. I encourage you to read the paper to learn more about those. Now, before going further, I'd like to mention that this problem we're considering does not exist in a vacuum. It's one of the oldest problems in statistics revisited with more modern considerations. And in particular, there is a long line of work dealing with similar or related questions. Here I listed only a few. Again, I encourage you to read the paper for a more thorough literature review. On this slide, the icons mean communication constraints, privacy constraints, or no constraint. So at this point, I'd like to give you a flavor of our upper bounds, namely the 3 algorithms we provide, 2 private coin and 1 public coin, and start with the private coin upper bounds. So our first algorithm works in 2 steps. The first step is to discretize the data. So the users observe a continuous sample from a Gaussian, but they can only send L bits. So what's a natural thing to do to discretize their observation? Well, they can just forget about a lot of information, just take the signs of each observation they make. So this goes from a Gaussian to a product distribution over bits, over -1,1 to the D. And the key observation here is like, of course, if the mean of the Gaussian was 0, the mean of that product distribution is still 0. But importantly, if the mean of the Gaussian was far from 0, if there was a strong signal, then the mean of that product distribution is still not exactly at least epsilon, but epsilon over 100. There's still some signal preserved in that in the bits, which is great. That way, it suffices to solve the problem over -1,1 to the D, which is, well, a discrete problem. Here comes the second step of the algorithm, which we call simulate and infer. Namely, each user can only send L bits, right? But now we've got D bits per user. Well, the first user can just send the first L bits of their observation. The second can send the next L bits of their observation, etc., etc. Once we get D over L users, we get D bits. And since it was a product distribution, with these D bits, we can actually reconstruct one truly good sample from that product distribution of a -1, to the D. Now, it's a known fact that for the mean testing problem over binary distributions, square root D over epsilon square samples suffice to test our problem. Well, that gives the sample complexity I claimed. D over L to get samples times square root D over epsilon square samples, which is what we need, and that gives the D to the 3/2 over L epsilon square. The second protocol, the D over epsilon to the 4, is even simpler. Here we're not even going to use all the bits we can send. We're just going to send one bit. So we have a Gaussian. We want to test the mean of the Gaussian. What's natural? Well, let's just compute the empirical mean. So each user will compute the empirical mean based on their one single observation of that high-dimensional Gaussian. And then, well, they're just going to threshold it appropriately for some tau that depends on D and epsilon. And they're going to just send 0 if it's below the threshold and 1 if it's above the threshold. And you can show that with this test, D over epsilon 4 samples suffice, which means D over epsilon 4 users. So that's all for the private coin protocols. Let's switch to the public coin upper bound, the D over square root L epsilon square. Here again, we start with Gaussians and we can only send a few bits. So it'd be good if actually in the case where mu is where there is a strong signal, mu is significantly far from 0, the first L bits of mu add some discrepancy from 0 we could use, because then each user could just focus on these first L bits and basically do as before. It's not true in general, though. There is no reason for the discrepancy to be in the first L bits. But if we randomly rotate the space, then with high probability, it will be the case that some significant portion of that discrepancy will be in the first L bits of the observation, which is great because we have public randomness, that shared random seed. So the users can use that to pick the same uniform random rotation of the domain, independently of everything else, and then apply that same rotation to all their observations. And then, again, we can show that in that case, with high probability, the first L coordinates of their observation after that rotation will preserve enough of the distance for us to use a simple protocol, and things work out, and we will get, again, that D over square root L epsilon square users. So that's, again, all very quickly for the upper bounds. I'm going to switch to the lower bounds in the little time I have left and explain what we get and why we don't get more and why we hope and conjecture it is actually the right answer, those bounds I mentioned. So what we show is, focusing on two of them, a lower bound against any public coin protocol, which is D over L epsilon square users are necessary. We also saw that for a restricted but very natural class of public coin protocols, symmetric protocols, D over square root L epsilon square users are necessary, which matches our upper bound. And we conjecture all those to be tight. The lower bounds we prove are actually evidence of this. We provide more evidence and discussion in the paper. I encourage you to read it. So why is it hard? Well, again, I don't have much time. So at a very, very high level, the idea is we know and how to optimally handle quantities of the form expectation under standard Gaussian of x times an arbitrary function of x, which corresponds to the probability to output a given message when seeing that x, which is great. And we know how to optimally handle that. But in this case, we must handle nonlinear things of the form expectation of e to the x times that arbitrary function, which seems like a small difference. We could just use a Taylor expansion and look at the first few terms, but Taylor expansions just won't cut it. It doesn't work. I'd be happy to talk about it much more in detail, either by email or offline, but that's the gist of the technical difficulty. And which brings us to the conclusion. As a future direction, an obvious one would be, well, establish our conjecture, establish that the bounds we establish as upper bounds are actually tight. Then I think that's doing that and then celebrate. And yeah, thank you for attending, and I'd be happy to answer questions offline or by email. Thank you.